In this lecture, we discuss about gamma function. The gamma function was first introduced by Leonard Euler in 1729 as a generalization of the factorial function for non-integer values. Gamma function was first introduced by Euler in 1729 as a generalization of factorial function. What it means? It means that suppose we have a factorial of 3, we know what its value is. It is 3 into 2 into 1. If we have factorial 4, we are also able to know what is its value, 4 into 3 into 2 into 1. But if we have given 3 by 4 factorial, so what is the value of this? So definitely we are not able to find out the value of factorial 3 by 4 as a factorial function. So this factorial can be given in terms of gamma function, which was introduced by Euler. Euler used an integral representation to extend the factorial function, but it was later formalized and named the gamma function by Andrine Marie Legendre. Its modern notation, gamma of n, was also popularized by Legendre in the late 18th century. The function is now a cornerstone of mathematical analysis and appears in many areas such as calculus, complex analysis, and physics. Extensions of gamma function such as beta function and the incomplete gamma function have also played significant roles in mathematical developments. Gamma function is called as Euler's integral of second kind. It is called as a Euler's integral of second kind. It is denoted by gamma of n and given by gamma of n is equal to integration of e to the power minus x to the power n minus 1 under the limit 0 to infinity with respect to x, where n is always positive number. Let us see some properties of gamma function because this is the new function which we have defined right now. So let us see some properties of gamma function. The property number 1 is gamma of 1 is equal to 1. So let us prove it how gamma of 1 equal to 1. So we know that what is gamma of n equal to? Gamma of n equal to integration of e to the power minus x to the power n minus 1 under the limit 0 to infinity with respect to x. Let us put n equal to 1. Then gamma of 1 equal to 0 integration of e to the power minus x. This n is substituted by 1. So 1 minus 1 x to the power 1 minus 1 under the limit 0 to infinity or with respect to x. So we know that this x to the power 0, which is 1, and we know that what is the integration of e to the power minus x. E to the power minus integration of e to the power minus x is e to the power minus x divided by minus 1 under the limit 0 to infinity. So if we substitute the upper limit and lower limit, minus sign we have taken outside, e to the power minus infinity minus e to the power minus 0. E to the power minus infinity is 0. E to the power 0 is 1. So this is minus of 0 minus 1. So this minus and minus will become plus and we have the answer 1. Hence, gamma of 1 is equal to 1. The second property is based on the reduction formula of gamma function. So gamma of n plus 1 is equal to n gamma n. Let us prove this result. So we know that gamma of n is equal to integration of e to the power minus x to the power n minus 1 under the limit 0 to infinity with respect to x. Now let us replace this n by n plus 1. So we have integration under the limit 0 to infinity of e to the power minus x x to the power n plus 1 minus 1, n plus 1 minus 1. So x to the power n, we can write down integration under the limit of 0 to infinity, under the limit 0 to infinity of e to the power minus x, x to the power n with respect to x. Now let us use the integration by part. And now integration part, if we apply, the x to the power n is the first function because it is algebraic function. So x to the power n, integration of e to the power minus x is minus e to the power minus x under the limit 0 to infinity minus derivative of x to the power n is n x to the power n minus 1, and again integration of e to the power minus x is minus e to the power minus x with respect to x. So it can be written as x to the power n upon e to the power x under the limit 0 to infinity plus, we can take this n outside, this minus and this minus will become plus, integration of e to the power minus x, x to the power n minus 1 under the limit 0 to infinity with respect to x. But we know that what is the limit of x to the power n upon x e to the power x when x tending to 0? This is 0, so the left hand side is 0. And now we have the only this term is remaining. But if we see, this is nothing but gamma of n. This is nothing but gamma of n from the definition. Just look here. So we can write down 0 plus n gamma n, or gamma of n plus 1 is equal to n gamma n. Property number 3, gamma of n plus 1 is equal to n factorial, where n is a positive integer. So let us try to prove this result also. So we know that gamma n plus 1 is equal to n gamma n. So we can also write down n, n can be written as n minus 1 plus 1, right? This minus 1 plus 1 will cancel. So this can be written as, by using the same formula, we can write down n into n minus 1 into gamma n minus 1. Similarly, it can be again written as n into n minus 1 into n minus 2 into n minus 3 into n minus 4 up to 3 to 1. So we can write down like this. Ultimately, we are able to write down n into n minus 1, n minus 2 into n minus 3 up to 4 into 3 into 1, 2 into 1. So it is nothing but n factorial if n is integer. So this is the relation between gamma function and factorial function. Property number 4, gamma of 0 is equal to infinity. So let us try to prove this one. We know that gamma n plus 1 is equal to n gamma n. Let us, what is gamma n? Gamma n is equal to n gamma n plus 1 upon n. Now let us put n equal to 0. Then we have left hand side is gamma 0. Gamma 0 is equal to, this is gamma 0 plus 1 upon 0. So gamma 0 plus 1 is gamma 1 divided by 0, and gamma 1 is equal to 1. So 1 divided by 0 is not defined, means it is infinity. So that's why the gamma of 0 is equal to infinity. This is the property number 4. Let us see the property number 5. Gamma m into gamma m plus 1 by 2, which is equal to root pi upon 2 to the power 2m minus 1 gamma 2m. This is called duplication formula. So we are just taking its properties. Property number 6, gamma p into gamma 1 minus p, which is equal to pi upon sine p pi, where p lies between 0 to 1. So we can also use this formula many times. And the property number 7 is gamma 1 by 2 is equal to root pi. So let us prove this gamma 1 by 2 as root pi using the property number 6. Let us use the property number 6 to prove this result. We know that gamma p into gamma 1 minus p is equal to pi upon sine p pi. So if you put p equal to, putting p is equal to 1 upon 2, we have gamma 1 by 2 and gamma 1 minus 1 by 2, which is equal to pi upon sine p is equal to 1 by 2 pi. So sine pi by 2. But we know that what is sine pi by 2? It is 1. and gamma 1 by 2, and it is again 1 minus 1 by 2 is 1 by 2. So which is equal to pi upon sine pi by 2 is 1. So we have gamma 1 by 2 whole square is equal to pi. So what is the value of gamma 1 by 2? It is nothing but root pi. So this is the very important value of the gamma 1 by 2, which is useful mainly in the uh, complicated values to find out the gamma function of that type of complicated values. So we should learn that what is the gamma 1 by 2? It is nothing but root pi. So let us just revise the different properties of gamma function once again. Gamma of n equal to integration under the limit 0 to infinity of e to the power minus x, x to the power n minus 1, where n is equal to n is greater than 0 with respect to x. Gamma of n equal to 1. Gamma n plus 1 is equal to n gamma n. Gamma n plus 1 is equal to n factorial, where n is positive integer. Gamma of 0 equal to infinity. Gamma m into gamma m plus 1 by 2, which is equal to root pi upon 2 to the power 2m minus 1 into gamma 2m. Gamma p into gamma 1 minus p, which is equal to pi upon sine p pi, where p lies between 0 to 1. Gamma 1 by 2 is equal to root pi. So these are some properties of the gamma function. While solving some examples based on the practical applications of gamma function, at that time we should learn all this formula. Then the solving of that type of question is very simple. Now transformations of gamma functions. So there are some different forms of gamma function that can be also considered as the alternate definition of gamma function. So first we know that what is gamma function? Gamma of n equal to integration of e to the power minus x, x to the power n minus 1 under the limit 0 to infinity with respect to x, where n is greater than 0. Now it can be also written as gamma of n is equal to 2 times of integration of e to the power minus x square, x to the power 2n minus 1 under the limit 0 to infinity with respect to x. So this is alternate definition of gamma function. Let me write down third condition. Integration of e to the power minus kx into x to the power n minus 1 under the limit 0 to infinity with respect to x is gamma of n is divided by k to the power n. So now instead of suppose that here the power exponential function has only e to the power minus x. If this e to the power minus x is replaced by kx minus kx, then the power of k to the power n is divided by gamma function. The fourth alternate formula for gamma function is gamma n plus 1 is equal to integration of e to the power minus y whole to the power 1 upon n e to the power minus y to the power 1 by n under the limit 0 to infinity with respect to y. So these are some alternate transformation of gamma function, which is also useful when while solving some numerical problems. And the last one is the gamma of n equal to integration of log 1 upon y whole to the power n minus 1 under the limit 0 to 1 with respect to y. So these are the four different transformation of gamma functions. Now the next question comes that what are the applications of gamma functions? So let us take some applications of gamma function. The first application is extension of factorials. So gamma function is used to calculate factorials of non-integers and complex numbers. The second application is probability and statistics. Gamma function appears in the probability density functions of the gamma distribution, beta distribution, and chi-square distribution. So this is also useful in the probability and statistics. The third application is in physics. It is used in quantum mechanics, statistical mechanics, and the calculation of partition functions. The fourth application is in spatial functions. The gamma function generalizes many spatial functions such as the beta function and the incomplete gamma function. The fifth application is in calculus. Gamma function solves integrals involving exponential and power functions. The sixth application is in complex analysis. It plays a critical role in residue calculus and contour integration. The seventh application is in engineering. It is used in signal processing and control theory for modeling time and frequency responses. The eighth is the machine learning. It appears in the derivation of certain loss functions and distributions. The ninth one is the differential equations. It provides solutions to many ordinary and partial differential equations, especially in boundary value problems. And tenth and the last application of gamma function is in number theory. It related to the Riemann zeta function and analytical property of prime numbers. So these are some applications of gamma functions. Thank you.